Okay, I think we'll get started. So today we're going to talk about the times we need to break a higher order zero at zero. So let's consider a normalized Blaschke product where we have a higher order zero at z equals 0. So we're going to say m is greater than 1 here. Now, this is still normalized in the sense that when we put 0 in, we get 0, and when we put 1 in here, we get 1. So we are normalized in that sense. But when we're talking about things that involve finding the critical values, which is setting the derivative equal to 0, it can be problematic to have a 0 that is a multiple. Now, that can be true also here, but you can always do Mobius transforms to move that to 0 and then do the technique that we're going to talk about here. So we're going to show 2 examples of this technique and then a little quicker example where we can do something even a little bit faster. Okay, so the idea here is that we use the fact that composition, either pre-composition or post-composition with a Mobius transformation, still results in a Blaschke product. So we'll have a Blaschke product at the beginning, we'll have a Blaschke product at the end, and we're just going to convolve or composite with one Mobius transformation. This should be a P1 and a P2. Okay, so we're going to choose a particular point and a particular point here, and so what we'll go through is how we do that. Okay, so let's take the simplest possible example, and that would be z squared. So this is indeed a Blaschke product. It's normalized in the sense that when we square 0, we get 0. When we square 1, we get 1. But it does have this second order 0. So the derivative is also 0 at 0. And sometimes we don't like that. We want to move that. Okay, so we're going to just choose an arbitrary point P, 1, to be 1/2 here. And this will turn out to be a pretty convenient point. So we'll plug in a 1/2. We get a 1/2 squared, so we get a 1/4. And that will determine our P2. So that locks in our P2 there. Then we will go ahead and plug this in. So here and here, right, is this part. And then here we're seeing that second point come in. And so our new Blaschke product A is written this way. Now, it doesn't appear like it's a Blaschke product here, but we know it has to be because of this idea. So we can simplify this down, and when it simplifies, it actually splits nicely now into a Blaschke product that has indeed a first power here on z. So we've accomplished what we want to accomplish. Now let's check to see if it's still normalized otherwise. So let's plug a 0 in. And of course, we're going to get 0. And let's plug a 1 in, and we basically get 1 minus 4/5 over 1 minus 4/5. So that's equal to 1. So indeed, we have now a new normalized Blaschke product where we have removed the degeneracy of that first, or of the 0. Okay, well, let's do one more. Let's do z to the 3rd power. So we plug in a 1/2 and we get a 1/8. So this part here is the pre-composition with a Mobius transformation, and then here's the post transformation. So there's where the 1/8 is coming in. Now, it takes a little bit of working out, and I used Mathematica to help me factor this, but it does factor then into a Blaschke product, and as it should, but we see now the explicit factors. So there's zeros at z equals 0, z equal 4/5, and then z equals 1/13 times 5 plus or minus 3 root 3i. And that's just what it turns out to be. And there's our new Blaschke product that indeed has that. And it does actually factor down to 1. We can kind of see that happening here because this will be a 1, this will be a 1, 1, 1, 1, 1, and all those will cancel directly so that a of 1 is equal to 1. All right, a little bit quicker here. So let's imagine we have this. Notice now we can't choose 1/2 because we don't want to put, we want the point to be arbitrary, but we don't want it to be another 0 because 0 is 1/2. But what we can do is we can do a switcheroo here. We know that we can compose this with a Mobius transformation, and let's use a Mobius transformation that puts 1/2 at 0. So if I put a 1/2 in here, right, that'll be 0. So I'm going to use this Mobius transformation, and this is how we can move 1/2 to 0. And basically then we're going to flip-flop both of these. So I will plug this in here, and notice I can write that this just becomes this squared, and then this is precisely z. So we're making this is tau z. So this does our flip, and so then we have that now in the form of a Blaschke product where we have moved that degenerate 0 away from 0, if that's what we wanted. All right, so this is kind of a quick video just to show this extra step. So last video we talked about normalization. This video we'll talk about breaking the degenerate zeros if we need to.